So a little bit more about Python. And obviously, we're not covering the whole language here, but the idea is to cover at least a little bit about classes. We'll have more to say about Python later in the course, but we'll have to wait till after the midterm for that. And then, we're next going to be talking about client server, JavaScript, all that sort of thing. We won't finish with the second topic. So when we last were talking about Python, we were talking about classes and how classes are an object in Python. So you can say, class C, A, that sort of thing. Put some code under here. This defines an object called C that in some sense is the class, right? It's not like C++ where the class is in your head. It's actually an object that you can compute with. Couple of points here. Python allows multiple inheritance. You can have two parents, right? Or two superclasses. And then the question comes, what happens when your parents fight? When they disagree with each other? The common problem with multiple inheritance. What's the rule in C++? You guys are C++ experts, right? Take note. They talk about inheritance and you have two parents. Yes. Right, so here we have this situation, right, where C has two parents, A and B. And it could be that A has a parent W and X and that sort of thing. So C has grandparents. And if, here, suppose we have an object that we've created from C, and we say, okay, now let's invoke the M method of that object. Which M method do we use, right? So we first look here, right? And then in C++, the rule is, well, suppose there's an M up here and not here, then, we'll keep sort of, or suppose there's an M here and an M here, this one wins, the closest one wins, right? But I'm worried more about the following situation. Suppose there's no M here and no M here, but these guys both have an M, right? Now, which M do you invoke, right? So in some sense, the real problem is here. A doesn't define M. It has two parents that both define M. What's going to happen? And I'm not a C++ expert. I ran away from C++ in the 1990s and never looked back. But I've been told that in this situation, it's an error, right? You have two conflicting parents. You shouldn't do that, right? And so it's sort of an ambiguous call here. Which M do we call? I don't know, right? So the compiler will yell at you. Python uses a different strategy. What it does is it simply does a traversal of the ancestor tree. Depth first, left to right. Depth, well, height first, right? So basically it looks here first. If there's an M here, that's the M it calls. If not, it looks here. If there's an M here, that's the M that it calls. And then it just keeps going, right? So the order of parents matters. And if it doesn't find an M here, it looks here, and so forth and so on. If there's nothing up there, then it'll go look here. Let's say B's parent has two parents, X and Y. Then it'll look here again, but it didn't find it earlier, so it's not going to find it again. And then next it looks here. So that's the order that it looks in multiple inheritance. Right, so in some sense, you can think of this as being C has a superclass A, but in places where A has gaps, B can fill in, right? And that's a different attitude from C++, yeah. No, it's left to right order here, right? So if I put BA here, it'd look in B first. All right, So another thing that's different about Python compared to C++, but is more common in scripting languages like Python and JavaScript, is that this relationship, or even the set of methods that a class has, is dynamic. And you can change it as the program runs. That's not true in static languages like C++. So in particular, every class, a class is an object, right? So you can take a look at that class's dictionary. So if C is a class, it has a funny sort of instance variable. You can think of it as a class variable called __dict. And by convention, in Python, names starting with underscores are special. They're supplied by the system. You shouldn't mess with them unless you know what you're doing. But to some extent here, I'm going to tell what happens if you do mess with this. This is a dictionary. And what it does is it maps, the names associated with a class with their value, right? So in particular, if our class defines a method M, and there's some code in here, somewhere in this dictionary, you'll see something that says, hey, M has this value. And this value is going to be a method, right? It's going to be something like, it's going to be a function that's part of a class. Functions are values in Python, just like classes are. And what this means is, if you want to, you can mess with how the class is implemented, right? You can say something like this. Oh, underscores, sorry. And then all of a sudden, the class will have a new method, n, that you've defined dynamically, right? Assuming that the ... dots there is another method. So the definition of a class is something that you can change later if you don't like the current definition. Now, this is not a routine thing in Python. Normally, people just write code like this, and it just runs. The reason you start to play games like this is when you try to do sort of programs that generate other programs, right? You're trying to write a Python package that maybe takes an existing package and wraps, methods and sort of renames them and causes that package to do something differently. So that kind of meta programming is when you will start playing this game. It's not something that you'll do as a beginning Python program. All right. Continuing in that sort of meta programming scheme, you can define methods in your class with underscores in their name. And if you do, that will hook into how classes are used by Python. The simplest version of that is there's an init method, right? And here you can say self xy, right? This method will be executed immediately as an object is being created. So if I call C of 10, 19, this method will be executed with self bound to the newly created object. X is 10, Y is 19, that sort of thing. That's pretty routine. But there are other sort of methods that you can define that are built in to Python. For example, you can define how an object looks like when it's converted to a string by defining the string method, right? You can take any object, we can, let's see, oh, we can do this. And then we can say, let's print. Oh, the way print works is it takes your object, converts it to a string, and outputs the string. Well, you can define how that works if you don't like the default, which is kind of ugly, that sort of thing. This may help to explain a couple of methods that I talked about last time and kind of swept under the rug a little bit. If you'll recall, one of those methods was, if you have a list, you can sort the items in a list, right? And obviously, if that's a list of numbers, you just compare the numbers and use that to figure out which number goes before what. But suppose this is a list of objects that you've defined. It's a list of objects of type C. How do we compare sort of random objects? Well, inside class C, you can define comparison functions. So you can, in here, define a comparison function. Comparison method, I should say. Put whatever code that you like in here, and that will tell Python how to compare elements of your class to any other object that you like. And by convention, this returns -1, or a negative number for less than, 0 for equal, and +1 for greater than. So you can return any one of those three values to sort of tell Python how the comparison works. Similarly, particularly for immutable classes, you can improve the performance or change, well, I'm not saying this right. This sort of fits into another thing, which is how do dictionaries work, right? Suppose we do something like this, and then we say, let's use O as a subscript in a dictionary, right? If you're going to do this, you want to have a good hash function, because internally dictionaries are defined in terms of hash, and you can specify that by saying, oh, well, here's a good hash function. This should return an integer of some sort. And that integer should be, basically, you walk through the contents of the object, the layout of which you know, and compute an appropriate hash value for those contents. Yes? Well, it's a three-way comparison, because you need to be able to say whether it's less than, greater than, or equal to, right? And it's kind of a pain, to be honest, because suppose you have something that acts like floating point, right? Floating point numbers are kind of strange, because if you compare two floating point numbers, the answer could be less than, equal to, greater than, or question mark, right? Because floating point numbers on almost all current machines have special NaN values that represent computations that have failed. If you compare a NaN to any number, the answer is, I don't know. In fact, you can compare the NaN to itself. The answer is, I don't know. So for objects like floating point numbers, this approach kind of falls down, right? Because we want to be able to return sort of 4 possible values rather than 3. For that reason, Python will let you do something like this. Right? This is the less than function, right? And when you just want to know whether one object is less than another, it will invoke this function, and this returns a Boolean. It's either true or false. And that way, you can accurately specify what happens with a NaN. A NaN never compares less than anything. You don't have to worry about, having to decide whether a NaN is greater than or less than. Some Python sort of built-in operations really prefer CMP, because this is going to, be more efficient to call CMP to compare two values, and then you don't have to say, is it less than or equal to, right away. other Python operations like this, right? You just compare two values of type C, that sort of thing, then it can invoke the LT operation underneath. All right. So see, what other operations do we have? Oh, an important one. This one may sound a little weird, but that's all right. There's a non-zero method that you can define. And Python uses this method whenever you write code that looks like this. Right? Here, you're just saying, should O count as true or not? And, you know, none counts as false. So for many objects, that's good enough, right? If it's not none, it's an object, and this if should go. But some objects, like objects representing numbers and that sort of thing, you may want to have, you know, a set of zeros that you want to say, oh, this should count as false. And you can do that with this non-zero method. You can even define stuff like this. That is, if in the source code, you're adding numbers in Python, you can specify how that should work with an add method. And in some sense, this is how Python does what C++ would do with overloading. Python does by redefining sort of the built-in methods. Add, there's, you know, one, multiply, subtract, all that sort of thing are also in there. All right. So I guess what I'm trying to say here is not so much the specific details of these particular methods, is Python's really flexible in how you interpret the code. And you have to be, in some sense, careful. If you go read somebody else's Python code and it looks like they're just adding numbers and comparing numbers and sorting numbers, well, that same method could be used to add, compare, and sort sort of arbitrary objects that they've defined with, you know, code like this. Any questions about overloading or redefining things? In some sense, it's almost too much power. Don't abuse it, right? Like suppose, I don't know, suppose your hash function prints things out. That's probably not a good idea, because now every time you try to look up something in a dictionary, you're going to get some output. And most code that looks stuff up in dictionary assumes that there's no side effects in simply looking up something in a hash table. All right, well, enough of Python for now. We'll talk about packaging and all that sort of stuff later. It's really time to talk about client server, if only because that's what the current assignment is about. And I should warn you that things are going to be faster here on out. And faster in some sense, and faster in the sense that I'm not going to lecture so much about the details of JavaScript and that sort of thing. I mean, I'll talk about it, but I'm going to rely on you to learn the details on the own, right? So you sort of learn things like, you know, where do the curly braces go on your own in JavaScript? And the idea being that a big part of software construction is coming up to speed on new technology. And if you're not used to JavaScript, now's a good time to get used to it, right? The second thing is there's kind of a lot going on here. There's lots of underlying technology that you haven't seen before, at least not formally in our classes. Technology, sorry. And I'm kind of going to be talking about this as opposed to the syntactic details on how you manipulate the technology. A third thing is that you're doing a simple sort of student assignment here. It's in some sense quite much easier than homeworks 1 and 2, right? And I'm going to try to make up for that in the lecture by talking about some of the practical problems here in using this technology that you'll run into if you try to scale it up and do something big, but you're not going to see them so much in a very small exercise in homework 3. So these practical problems that are not an issue in homework 3. But since you're going to be using this same technology in your project, your class project, they will come up there, at least in some cases. And so I'm going to be kind of warning you about this, right? I'm going to be saying, watch out, right? Here's a danger sign, right? And so sort of focusing on performance issues or scaling issues that really aren't going to be an issue for the homework 3. But that's okay. You get to sort of see it in advance, I hope. To some extent, what we'll be looking at here, of course, is Node and React. Okay. Two technologies built atop, you can think of it as sort of JavaScript plus sort of POSIX, sort of an operating system. Doesn't have to be, plus a little bit of the shell. You're going to be sort of building a system that is based off of the files that we've talked about and a little bit of the shell and this new JavaScript notation. And there's going to be a lot of things in common here, right? That is, over here, many of the issues is you use the shell as a configuration language. We're going to see sort of the same issues here. A good chunk of getting a React application working correctly is going to be how to configure it and all that sort of thing. And another issue that comes up in both the base system here and the more advanced system is quoting issues. Figuring out how quoting works in the shell is a real problem, okay? It seems like a minor problem, but it can turn into a major one. Quoting actually gets to be an even bigger problem once you start using Node and React. And so I'm going to spend a little bit of time on that as well. All right, so enough interaction. Basically, or introduction, I should say. Basically, what we're talking about here is what's called a client-server system. And this is a major change in the software architecture between all the stuff that we've done in this class and all the stuff you learned in CS31 versus how a lot of practical applications are built, right? So it's, in some sense, a pretty simple model. Here's the client. Here's the server. They're different computers. They're different programs running on different computers. And they talk to each other over a network, right? And you can think of the network as just being sort of a wire connecting the client to the server. A more accurate depiction of the network, though, is going to be something like this. There's this weird thing here, network. If you look inside the network, there's a lot of connections and all that sort of thing. One possible abstraction is just to say, oh, that's kind of a messy thing. Let's just call that a cloud, right? Cloud computing. We're going to actually look inside the cloud and see a little bit of how it works in order to sort of grasp some of the performance issues involved, which are going to be the basis of a lot of the practical problems here. But before we jump into the details, I should say this is not the only model, right? In distributed computing. Right? With the client-server model, typically, in the simplest version, you have one client, but oftentimes you'll have multiple clients. And in your project, or I hope you'll be considering that possibility. But in this system, in some sense, it's quite simple. because in some sense, the server is in charge. Even though it's called the server, it keeps track of all the important state that's shared by the clients. And the way that the clients communicate to each other is via the server. And this approach, although it works very well, it has some nice properties, there's some scaling issues involved here, right? If you start having 1,000 clients or 1 million clients, you're going to start overwhelming any particular server. So there's some alternate approaches here. One is to try to scale up the server by having multiple servers, right? So you have the clients, and maybe a lot of them, they're talking via this network. And then you have a small, probably smaller number of servers that are pretty closely connected to each other. And the idea is they spread the load, right? This way, if you overload a single server, well, another server springs into action and starts handling requests like that. A more general model is a peer-to-peer approach. Under this approach, the different machines on the network aren't segregated into client and server categories. Instead, every node on the network is potentially either a client or a server, right? So you have a network like this, and then you have a whole bunch of peers. And each one of these peers maintains part of the state of the system, but there's no single entity, there's no single sort of server that keeps track of who the users are and all that sort of thing. The responsibility for keeping track of all that stuff is distributed amongst all the systems, right? This approach could scale better, right? Because here there's no single server that's going to get beaten up and overloaded and that sort of thing. As the number of computers on the network increases, they each share the load and all that sort of thing. The downside of the peer-to-peer approach, though, is if no peer is in charge, then how do you know which peer to ask a question of? If you have a question, like if they maintain a database of locations, which peer is in charge of which location? Another possibility is to take this client-server approach in which the clients are asking the questions, right? And the server is sort of provides the answers, and flip it around, right? And in a flip around approach, you might sort of have a primary node, right? And its job is to generate questions. And then you have a network here. You have a bunch of secondary nodes here. You can think of them as being sort of like worker bees in a beehive. And their job is to get questions and provide answers, right? This approach is popular in machine learning, where you have a big learning job and you split it up into a bunch of sub-jobs, and you hand off each sub-job to each particular component. Now, all of these approaches are widely used in distributed computing. You can do all of them with Node and React. I would have to say that client-server is sort of the wheelhouse for Node and React, but the underlying technology can be used to build any of these approaches. And I haven't really come up with all of the possible approaches here. There are even more besides these 4 major ones. We'll be focusing on this one, but don't forget about the possibility of others. And actually, if you want to do one of the others in your project, that's going to be more ambitious, but that would certainly be a good sort of project to do. Now, what's new about any of these approaches? We'll be focusing on client server in terms of performance issues. Of course, you still have all the performance issues that you saw in CS31. So you have to worry about, is this an order n algorithm, order n squared algorithm, and all that sort of thing. So the usual sort of things within a computer still apply. But there are new performance issues that come up because your application is distributed. If you have to ask a question and get an answer back over a network, that's going to slow you down compared to if you have the answer locally. The two major categories of performance that sort of come up over and over again in distributed computing that don't come up so much in centralized computing are throughput and latency. Well, I guess they do come up in centralized computing, but they're a bigger deal in decentralized. All right, so by throughput, I mean, how much work is the total system doing, over time? So you can think of it as sort of how many sort of queries per second, assuming it's a database-like system, is the overall system doing, right? Your goal in increasing throughput is to, support as many clients as possible by having this server be able to sort of take lots of requests and generate lots of responses, right? And the total number of responses it generates per second is the number that you're interested in. The second number is more from the point of view of the client. This is sort of a server issue, right? Is a throughput issue. The second one is more of a client issue, which is the latency is how much time does it take between the time a client asks a question and the time the response comes back, right? This is, what's the delay between a request and a response? Right? From the client point of view, you want the latency to be as low as possible, right? And from the server point of view, you want to sort of be able to satisfy as many requests per second as possible. Now, at first, you might think that these are just two sides of the same coin. A system with better throughput figures will be a system with better latency figures, right? Because it'll be a higher performance system. But that's not true. In fact, to some extent, these are competing goals. Not always, but often. You can improve the throughput of your system by making the latency worse, right? So for example, what a server can do is it can get several requests and keep getting more and more requests until it gets a big batch of requests. And then it can take the requests that talk about California, let's say, and do them all at once because it can have Californian information in its RAM. And then similarly do the same thing for Washington and Oregon. That will increase its throughput because as it does that batch of California requests, it'll do them very quickly. But it's going to hurt latency because the request that comes in about Utah is going to have to wait until the next Utah batch is sort of approved to be answered. Right? So oftentimes you're trying to sort of make your server more efficient, and you do, but you're going to hurt the average latency of requests. Conversely, if you try to tune your application, have really fast latency, like it's a video game service or that sort of thing, you're going to find that you have to do stuff on the server side that's not very optimal. You're going to hurt throughput to make the latency good. Now, this sort of thing is sort of going to be sort of an issue over and over again. So to some extent, what we can think about here is some sample strategies for improving these performance, right? And I've already sort of told you the sample strategy for improving throughput, right? Which is to batch requests. Don't handle requests when they come in immediately. Wait for a bunch of them come in so that you can sort of improve performance on the server by doing them in the proper order. Right? And so, in some sense, this really means you do out of order execution. And doing them out of order means you can do more of them per second. For latency, a standard tactic is you're on the client, you want to get an answer fast, and the way you get that answer really fast is you don't send the query over to the server at all. Instead, you reuse the answer to a question that you asked recently. So if the user wants to know what's the temperature in Westwood, and you've already sort of asked what's the temperature in Westwood 5 minutes ago, you just reuse that temperature without bothering to ask the server over and over again. So a standard solution to make latency better is to use caches on the client side. Right? The client will remember recent answers and use them to answer related or identical questions later without bothering to consult the server. Now, yes, question.
We know that the duration of the end of the question won't change for enough time. So how do you rely on the pattern on the client?
Oh, well, that's basically, that's a very good question, right? So to some extent, what's going on here is we're worried here about performance, right? But there's going to be some correctness issues that come up when you start doing that, right? Right? And if we take a look at this very standard tactic here, the correctness issue is, what do you do about stale caches? Right? How do you deal with the fact that the answer that you have about the temperature in Westwood, well, it was valid 5 minutes ago, but all of a sudden, I don't know, an iceberg hit Los Angeles or something, and the temperature has gone down. Other question? Or was it, yes?
That's adjacent to it, like memory.
Mm-hmm.
But I was curious to know, like, if the client can catch queries of similar nature as well, so that like it's like a catch-all.
In other words, if I'm understanding you right, the user originally asked, what's the temperature in Westwood? But what the client thought to itself, well, I'll bet you the user will want to know what the temperature is in Culver City pretty soon. So it goes and proactively asks that question of the server, even though the user hasn't asked it, right? So it preloads its cache. And yeah, that's another performance strategy, but it also, it's going to have sort of that's going to sort of, have the correctness issue about stale caches, but it also has a performance issue, right? So here, suppose you do aggressive caching, right? And do what you're describing. You can think of it as like prefetching. You grab stuff out of the server, even though the client hasn't asked for it yet, because you figure the client's going to ask for it pretty soon. You can go overboard with that, right? You can ask for way too much information and overload the server and overload the network and all that sort of thing. And so that's going to be a performance issue. How aggressive should you be? You don't want to be so aggressive that your performance gets worse. All right, but it also introduces more of this issue, right? The bigger your cache is, the more hassles you're going to have with stale caches, right? And from a correctness point of view, this turns into a problem that's called cache validation. Is there a way that you can check whether your cache is up to date cheaply without having to actually refetch all the data? Right? If you can do that, then you get sort of a compromise, right? You get something that will let you, attack the latency problem without, making correctness go kaflooey, right? If you have an appropriate cache validation technique. This sort of problem comes up over and over again in client server systems, and we're going to see it come up in the technology that you're using in this class. To some extent, to understand these issues, CS35L in some sense is an intro to CS111, the operating systems course, and a little bit of the database course and a little bit of the other thing. Well, today, to some extent, is an introduction to our networking course, CS118, because in order to understand what this cache validation problem turns into in your application, you're going to have to know how the underlying network works. All right, so let's take a look at the internet. And that's the technology that you'll be using to do your homework, right? But I also want to look at some alternatives as well. Because it doesn't necessarily have to be this way, at least in all distributed applications. And it's good for you to see some of the alternatives, even if we're going to mostly be using the internet. Before the internet, we had the phone system for our sort of major communication system, the telephone system. And here I'm talking about landlines. And the telephone system operated on what's called circuit switching. Circuit switching has the following property. If you are trying to talk via traditional landline from, say, Westwood to Brooklyn, New York, right? Here we are in Westwood. Over here is Brooklyn. Right? The way you're going to do it is you take your phone and you run a wire to what's called a central office, or CO for short. The central office is a bunch of electromagnetic switches, and there's a whole bunch of wires that go into the central office, one per phone. And the central office you're going to have another one here in Brooklyn. These wires, for technical reasons, can't be too long, right? You're not going to have them be 10 miles long. They have to be shorter than that. Now, these two central offices have to talk to each other. And the way they talk to each other is, well, here's sort of a switch in downtown LA. Here's a switch in let's say, I don't know, Manhattan. And again, these are physical wires. And these switches will talk to each other. Here's a switch in Phoenix. Here's one in, I don't know, Trenton. And there's a path of switches that goes all the way across the country. And when you're talking, you've got a pair of wires sort of connecting the two speakers that crosses the country. Now, there's a whole network of switches. There's a whole bunch. We could have gone through Tucson and all that sort of thing, right? You see, or we could have gone through Chicago. But the point is that when you set up the conversation, you set up a particular switch path. And while you're talking to Brooklyn on this traditional phone system, you've got these wires. Nobody else can use this set of this set of wires that connects you across the network, right? So a nice property of circuit switching is that while you're conversing, you have the wires reserved. Nobody else can use them, which means your conversation is guaranteed to sort of go through unimpeded, right? So there's no glitches in your conversation. Now, of course, there'll be exceptional conditions. Maybe a tree falls over on this pair of wires between these two switches. In that case, the phone goes dead, and then your conversation drops. You get a dial tone, you say, oh, I got to redial, and all that sort of thing. But those are rare. Normally, your conversation just works. Okay? Question? And not the traditional system. If one of these went down, you basically, your phone conversation ended. Eventually, this central office would figure things out. It'd give you a dial tone because the thing went dead. And then you'd make another call. And when you do the call, all these switches set up, they try to arrange to have a live connection. So you'd call, and then you'd be able to talk to Brooklyn again. Yeah, each call has to sort of decide which of these things. So there's a complicated algorithm that the phone system maintain of figuring out, which switch goes where and all that sort of thing. The end users didn't know about any of this, right? Because the telephone just talks to its central office, and that's all it talks to. Question? Oh, yes. So if there's too many people that want to use, say, I don't know, this connection, right? The next person who gets a call won't get this connection, they'll get another connection, right? If the circuits are overloaded, so then when you try to make a call to New York, the central office will tell you, I'm sorry, you can't call New York right now, the circuits are busy, right? So you either got a call and you got a reservation, or in the extreme case, you didn't get through and then people complained a lot and the phone company would go install more wires, that sort of thing. All right, so some nice properties about this approach, but there's a downside. And the downside is it's incredibly inefficient. We're getting reliability, but it's at the cost of basically, renting a pair of wires all the way across the country, and most of the time, those wires were sitting unused, right? Because, most of the time, only one side is talking, the other side's listening. So only one of these pairs of wires is being used, right? I mean, in principle, both sides can be talking and they can both hear, but hardly anybody did that. So that's a factor of 2 right there. And in normal phone conversations, there are gaps between words and between sentences and all that sort of thing. So a downside of this approach is that it's inefficient. There's another downside that's a little less obvious, but it's definitely there, which is that, as was mentioned, if one of these switches goes bad, right, or maybe one of these wires gets cut, the whole call fails, and you have to restart the whole call. It would be nicer if the system were more robust and that, a glitch in one of these intervening switches didn't break down your entire conversation. If you could continue the conversation even when there's a temporary interrupt somewhere in between. This last consideration is what bothered the military in the United States in approximately 1960. It's the height of the Cold War, and we're worried about people attacking our communication system. And one way they could do it is they could, take out a switch, and all of a sudden, all these conversations would go down, and maybe some of those conversations would be, defense related and all that sort of thing. So there was an effort to build a better communication system, partly for robustness in the presence of armed conflict. And this attempt was done at the Rand Corporation in Santa Monica. Right? So a researcher named Paul Baran at Rand said, we need a different way of communication that's more robust than this, and also promises to be more efficient. Okay? So this is sort of Rand Corporation, and it's circa 1961, I think it was. And his central idea is what is now known as packet switching. And the basic idea is we can use this physical network, right? Don't tear down all these wires and build a completely new network. I want to keep using these wires. I just want to use them more effectively and more efficiently and more reliably in the presence of intermittent failure. Right? So with packet switching, when you want a conversation between Westwood and Brooklyn, right, you don't reserve a pair of wires between the two. Instead, you take your conversation, you break it up into small pieces called packets, and you ship packets out to the net and hope for the best, right? So you break your communication into small packets, right? And small is, of course, a relative term, but a reasonable packet size might be, say, a kibibyte, right? So now, if I'm in Westwood and I want to send a packet to Brooklyn, what I do is I just send the packet off to my central office and say, you know, send this packet to Brooklyn. The central office has a little bit of memory in it, a little bit of RAM. It will accept my small packet and then think, where should I send the packet next? And it may decide today, oh, let's send it to Reno, right? Reno will get the same packet. It will, that packet will say, please send me to Brooklyn, right? And Reno may say, oh, let's send it to Phoenix, right? So the route of the packet is decided dynamically. We don't decide at the head of time. In fact, the sender doesn't know the route and doesn't really care. And each individual switch in the system doesn't know where the packet will go after that switch deals with it. But eventually, you hope Phoenix will send it to Chicago, and Chicago will send it to, I don't know, Cincinnati, and Cincinnati will send it to Manhattan. And finally, it gets to the guy in Brooklyn. But the next packet I send might take a different route, right? Packet 1 went this route. Packet 2 might go down to, I don't know, Tempe instead. And then maybe to Chicago. But Chicago this time might send it to Toronto, and so forth and so on. In principle, every packet might be sent by a different route. Okay. Now, what are some of the pros of this system? From a military point of view, a big advantage of this approach is that if you're talking and, Reno gets hit by an artillery shell from the enemy or something, well, we can send packets this way, right? Our entire conversation won't be interrupted simply because a switch goes out. We won't have to restart the whole conversation. So one advantage of this approach is sort of robustness in the presence of an unreliable network. But there's another advantage which may not be as immediately obvious, which is that this approach is going to be more efficient. We'll have the opportunity to have less sort of time that the network is just sitting idle. When I send some packets here, I haven't reserved a pair of wires all the way across the network. Other people can use the same wires that I'm using. I can send 2 packets here, and then on this connection, there'd be the same packet, and then maybe packets from other users before we use our packet, right? So another advantage of this approach is sort of more throughput. Right? Throughput is what we want. We want to send as much data through the system as we can. We want to use the wires as efficiently as we can. And so the throughput is going to be improved this way. Question?
Would the latency also be improved, or does that depend on like, the actual location of the node?
Yeah, latency is probably going to hurt, right? Let's mention that as a minus. Worse latency. Why? Partly because under this approach, each switch has to think, right? It gets a packet, and then it has to think, where should I send this packet next? So at least there's the latency that it has to wait to finish to receive the packet before it can start sending the packet and all that sort of thing. So you're going to get more latency here. Under the circuit switching approach, this switch doesn't have to think at all, right? When you're talking, the audio signal comes in, it can go out immediately because there's an internal actual physical connection. So it will hurt latency somewhat. Question? Originally, when Baran was first developing this, he was thinking more about military conversations where you could deal with lower quality because you're shouting over the artillery shells, that sort of thing. They weren't getting telephone quality then. Nowadays, though, the performance of the network is good enough that you can run ordinary voice conversations this way. So Zoom operates this way, and it works just fine usually, right? That sort of thing. Okay, so questions about these 2 major approaches? Yes, in back. Louder, please. How would the receiver know who sent the packets? Oh, the order. Oh, yeah. You're going to have problems here that with circuit switching, the data is always, received in the order sent because it's an analog signal, right? With packet switching, maybe the packets arrive out of order. And that's going to be a real hassle. And we'll talk about that after the break. So let's start up again at maybe 5 past the hour. All right, so a little bit about packet switching. And switching basics, right? First off, by convention, most packets have two parts, sort of the header, which you hope is small, and then the payload, which you hope is larger. The header is sort of information that the network uses to figure out what to do with the packet. You can almost think of this as being meta information about the packet. It's overhead needed to make the network operate properly. For example, one of the things in the header is going to be, I want this packet to go to Brooklyn, right? Because if that information weren't present in the packet, we wouldn't know where to send the packet. The payload is going to be the data for the application. By and large, the network isn't going to care what's in the payload. It won't look at it. All it's going to do is ship that packet off to the destination, payload and all. Second thing about packets is there are three problems when you send a packet. The first problem, and this was alluded to just before the first half of the lecture ended, is you don't necessarily receive packets in the same order that you send them, right? Packets can be received out of order. And that can happen if they take different paths to their destination, and one path just didn't work out as well as the other one did, right? This is a common thing that happens, and applications are going to have to sort of deal with this. Second problem, when the network gets busy, or when there's some flakiness in the network, packets can be lost. You sent the packet, it arrived at Phoenix. Phoenix, the switch at Phoenix was totally overloaded and decided, I've just got too many packets. I can't deal with them all. Here's some more packets coming in. I don't have enough RAM to hold all these packets. And so it just drops. And that happens all the time, right? I mean, this is a very common thing, right? In fact, it's more common than this. The third one, and this is a little less common, but it can happen. Packets can be duplicated. That is, you can send just one instance of a packet, but the recipient can see two copies of that same packet. This usually comes because the network is misconfigured, or there's a switch in the middle that gets confused and sends it out twice because it thinks the first sending didn't work, and so it sends it out again, that sort of thing. Right. So we're going to need some sort of method that can sort of deal with this, right? And the way we're going to deal with these three problems are to use what are called protocols. The word protocol comes from diplomacy, right? If you want to, I don't know, talk to the Queen of England, I'm sorry, the King of England now, you can't just walk up to the Buckingham Palace and knock on the door. Even if you're the American ambassador, you can't just knock on the door and say, I'd like to talk with a king. There's diplomatic protocols. You have to first have one of your underlings send a note to one of the king's underlings, and then they have to exchange messages and agree upon a time and place and meeting and all that sort of thing. This same idea that you can't just send a packet to some other place sort of out of the blue also occurs in networking. And so the networking protocols are the rules whereby you can sort of arrange to talk to somebody else and be able to send them packets in such a way that you can solve these problems by having the appropriate protocols that deal with things like lost packets or duplicated packets. So these protocols can be complicated. as we'll see, there's a lot of issues that arise once you start trying to deal with these packets. And for that reason, the protocols are usually sort of engineered in their own right. There's a whole sort of set of engineering ideas that you can use in coming up with good protocols. And the standard approach that's used to manage this complexity these protocols are divided into layers. These are layers of abstraction or layers of protocol design. At the bottom layer, we have what's called the link layer. And the link layer is really simple. It's the protocol that one node on the network uses to talk to an adjacent node on the network. Right? So a link layer is used. We're sitting here in Phoenix. We want to talk to, I don't know, Tucson. And the link layer is what sort of low level, typically hardware level sort of protocol we use so that Phoenix can say, oh, here's the packet, it's coming. And Tucson can say, oh, okay, I'm getting a packet and all that sort of thing. That's the lowest layer of the internet protocols. And the link layer is going to be sort of point to point, right? And hardware oriented. At the link layer, we don't even know about packet switching because there's no switches. We have packets. We're sending a packet from point A to point B, but the idea that point B will then decide where to send it next, that's too hard for us. We're just solving the link layer issue. All right, the next layer above that is going to be what's called the internet layer. And this is the protocol that's used to basically get your packet from Westwood to Brooklyn, right? So the idea here is we have Westwood here, we have Brooklyn here, and Westwood will send a packet. This packet will have in its header, I want to get to Brooklyn. And the internet layer deals with what switches are supposed to do, or these switches are actually called routers. What a router is supposed to do when it gets a packet to make sure that eventually it ends up in the appropriate spot in Brooklyn. The internet layer is built essentially off of one major protocol, and it's not very sort of entertainingly named. It's called the Internet Protocol, or IP for short. And what the Internet Protocol is about is what goes in this fairly small header, what a packet is, and when you get a packet, what you should do with it. All right, the next layer is the transport layer. And in some sense, what the transport layer does is it attempts to replicate some, and maybe, or a good chunk of the functionality of the circuit switching idea, right? So the basic idea of the internet layer is you send a packet and you hope it gets there. And at the internet layer, you got to worry about problems 1, 2, and 3, right? The transport layer says, no, what this guy in Westwood wants to do is it wants to send a stream of data to Brooklyn. And sure, maybe this stream is implemented by breaking it up into packets and sending the packets and all that sort of thing. But at the at the transport layer, I want to think of it as a stream, right? So what the transport layer attempts to do is arrange to solve these problems, right? That is, you send packets at the lower level, but at this level, you will receive the data in the same order it was sent. None of the data will be lost, and none of the data will be duplicated. You'll just see the actual stream of data reliably and in the proper order. And many applications will assume that, right? I mean, if you're shipping a file from point A to point B, you don't want its contents to be scrambled in the middle. So you'll want to be operating at the transport layer. You'll want to have a set of protocols that will let you do this sort of thing. At the very top of this hierarchy is the application layer. This layer will supply a protocol that's going to be application dependent. And the particular application that you use will affect what protocol you'll pick here. A classic application layer here is going to be, the World Wide Web. They have a particular protocol built atop the transport layer that will let you ask for web pages and get web pages back and that sort of thing. But there's going to be other protocols besides the World Wide Web. For example, there's a file transfer protocol, which is designed to transfer large blocks of files as opposed to small web pages, and it is considerably more complicated because of that. And you can think of lots more protocols here, depending on the kind of application that you want to do. All right, so let's talk. I'm not going to talk about this. This is for I know there's at least one double E major in the house who will, kind of be expert in this. So this is sort of getting Wi-Fi to work or getting Ethernet to work. I'm going to assume that's a solved problem, even though it's not really. And I want to start talking about the internet layer. Okay, so the internet protocol has come out. There's been several versions. Because this internet didn't sort of spring out fully formed from the head of Zeus or anything like that. It's evolved with time. There are two versions of the internet protocol currently being used. IPv4, which is the one that, if I log into CSNET, I'm using IPv4 and all that sort of thing. It came out in 1983. And it was specified by a team containing John Postal of UCLA. And he was working in, Belter Hall at the time, something like that. And so basically, the idea behind IPv4 is let's see what a packet looks like. And in particular, let's see what a packet header looks like. And the protocol specified what goes into a packet header and what you should do with it. If you're a router and you see a packet, how you should use the information in that header to figure out what to do. So key component of IPv4 is what the header contains. So it contains first a length field. That seems pretty basic, right? You need to know how long the entire packet's going to be, so that you can store it and forward it reliably. It contains a protocol number. The idea here is that IPv4 wanted to be the base layer for higher level protocols, right? And so you wanted to be able to say which of these high level protocols we're going to use. All right, we'll have a protocol number sitting there somewhere in the header. We also have a destination address. Here, the idea is that every node on the network has a unique number associated with it. In IPv4, this number is a 32-bit integer. Conventionally represented as 4 bytes, each represented in decimal. So you'll write down this 32-bit something like this. Right, and what that really means is it's a 4-byte number, if you take this byte and, excuse me, treat it as an integer, a decimal integer, it's 192, 54, 239, and 17, that sort of thing. All right? That way, when a router gets a packet, it will know, where that packet's destined for. It also contains a source address, which is another 32-bit integer that says where the packet came from. So for example, if a router gets a packet and say drops the packet, it might want to send a packet back to the source saying, I'm sorry, I couldn't really send the packet, that sort of thing. And it can use the source address for that. Couple other things it contains. First is a checksum. This is a checksum of all the data in the header and in the payload. It's a 16-bit checksum. So it's, not perfect, right? What that means is if there's a bit error in transmission, the chance that a random bit error will be caught is, or will be missed is 1 in 2 to the 16. So there's a small chance that if you get a bit error, the checksum will still match, that sort of thing. All right. And then one other field is a time to live field, or TTL for short. This is a small field in the header that basically you can think of it as follows. Each time a packet goes through a router, so it makes a hop from one node to the next, subtract 1 from this number. When the number goes to 0, then drop the packet, right? So another way of thinking of it, if the number here is 12, that means this packet is willing to make a traversal across 12 routers. And once it goes past the 12th router, it doesn't want to go anymore. It wants to die. So you can think of it as the expected lifetime of this packet. Why do you suppose this is in the protocol? What's the point of TTL? Yes. Exactly right. You don't want an infinite loop in the system, right? And so this prevents the infinite loop. All right. There's a few other fields, but this should give you a feeling for what's going on. Now, this source address is kind of tricky, right? Because in theory, you could inject a packet into the network with a fake source address, right? Because it's just data, and you can, program your client to ship out the source address being, I don't know, the White House source address or something like that. What's going to prevent you from doing that? The protocol says, please don't do that, right? But that is the source of some abuses of the network. There's some obvious workarounds or attempts to fix the problem, but it is a problem, yes.
You also set the timer with a really high number and just send a bunch of packets.
Yeah, you can set the time. I think it's only an 8-bit number, so you can't set it to be something too large. But yeah, you can set time to live to be too high. All right. Other things that can go wrong? Well, you could send a destination address that doesn't exist, right? There's no node on the network with this particular IP address. That could be an issue. And so, we have to deal with the protocols for that. All right. So then there's a later version, which came out in 1998. Okay. And it attempts to do better than IPv4. And the major sort of change that it makes, or improvement that it makes, is here. Right? When IPv4 was designed, they thought 32 bits. That's 4 billion computers. There's no way in the world there's going to be more than 4 billion computers, right? So we can that's going to be a perfectly large address space. Well, we now have more than 4 billion nodes on the internet. So this number was too small. IPv6 grew the number to be, I can't remember now. It's either 128 or 256. Whatever it is, it's plenty big. Okay, so we have a larger address space. It made some other changes as well, but that's sort of the major innovation that it uses. And what is reasonably common on the network now is to have sort of some parts of the network are IPv4, but then there are other parts that are IPv6. And then there's sort of a gateway in between where the IPv6 network can pretend to contain some IPv4 addresses, and there are standard ways of translating between the two. Since we're at UCLA, which invented the internet, we have a bunch of IPv4 address spaces, right? We were early in on the address space sort of gold rush. And so we tend to run IPv4 because it's more portable, it's more efficient because it's smaller and all that sort of thing. But, you know, if you're building, I don't know, a new network in India or something, you probably have to use IPv6 because there's not enough IPv4 addresses left available yet. Yes?
Would there be like loss of information like an IPv6 network to network?
Yeah, you won't be able to use any of the new IPv6 features. So there are some features in here designed for you know, doing real-time applications and that sort of thing, and they're not going to work in IPv4. In practice, my impression is that a lot of the IPv6s are not being taken advantage of primarily because of this issue, right? You want to be interoperable, so you try to solve real-time, you know, issues in a different way, not the IPv6 way. But I'm not a networking expert. You need to, you know, talk to a networking expert to see the details there. Other questions about the internet layer? Yes. So the checksum, I think it's pretty straightforward, right? You can just think of the packet as being an array of 16-bit quantities, and then exclusive OR them all, and then take that exclusive OR and stick it into the checksum field, right? And that way, if there's a bit error anywhere in transmission, even if it's a bit error in the checksum field itself, the checksum won't match, and the recipient can look at the packet and say, oh, this is a bad packet, and then drop it. That's a common thing to do with a bad packet. I think the checksum algorithm is a little bit more complicated than straight exclusive OR, but it's pretty straightforward. It's not intended to be a cryptographically secure checksum or anything like that. It's only intended to, you know, to deal with, you know, inadvertent transmission errors, hardware errors, that sort of thing. All right. So we've, to some extent, covered the internet layer. I then want to talk about the transport layer. And there are two major categories of transport layer protocols. The first is UDP for user data datagram protocol. And it was designed by David Reed of MIT. And the basic idea is quite simple. This is a very thin layer atop IP. And the extra features that it provides are mostly having to do with, you know, figuring out which protocol we're talking about and all that sort of thing. So if you're using UDP, your application is going to have to understand that packets can be lost. So it's sort of like your program does a print statement, and it has to realize that the person who runs the program won't see the output, but maybe, right? You just cannot trust communications if you're using UDP, right? So here it's the app's responsibility to deal with, you know, packet loss and that sort of thing. Packet loss, duplication, etc. Okay, so this is a very easy protocol to implement atop IP. So from a networking point of view, it's a nice protocol. It's very easy. Oh, I support UDP. But it's bad for applications. Many applications, don't want to do this. You send the message, you might not receive it. That makes your application harder to do. So fairly early on, the internet algorithms people came up with TCP, which is short for Transmission Control Protocol. And this is originally from work by Vint Cerf, who was an UCLA alum. At that point, he was at Stanford. And Bob Kahn of Princeton. And the basic idea of TCP is built atop IP. So it's sometimes called TCP IP. And it provides a protocol that lets applications have the illusion that they have a reliable stream, right? So it provides sort of a reliable, ordered, and error-checked stream. By reliable, I mean, if you send data via TCP, it's going to get to its destination, even if some packets are dropped in the middle of the operation and all that sort of thing. And because of this, TCP IP does the following things. First, it divides a data stream into packets. So one of the things that you'll do as part of the TCP IP protocol, for example, is you'll negotiate packet size. You'll figure out the size of the packet that you want to send. Sending very long packets sounds tempting, but a lot of hardware won't deal with it. So you might negotiate what's the largest packet we can send reliably at this point in time, that sort of thing. It deals with retransmission. If a packet gets dropped, TCP IP, the protocol layer, will figure out, oh, I need to resend that packet, right? Because the recipient never got it. It deals with reassembly. Since the recipient can get the packets out of order, TCP IP tells the recipient, oh, you got the packets out of order. Please reassemble the packets in the proper order to get the output data stream matching the input data stream. And last, and certainly not least, because this is in the actual sort of name of the protocol, transmission control, is TCP deals with a common problem with UDP. And that common problem is you have a greedy sender. The greedy sender says, I want to get as much data to Brooklyn as I can. So I'm just going to pump packets into my central office at Westwood as fast as it goes, right? I got, a gigabit connection. I'll just send a gigabit per second worth of data. Well, that's not going to work if you don't have a gigabit of connection all the way across the country. You'll just swamp your local central office with data and it'll drop it. But now it's doing a lot of work just to throw data away. So what the TCP deals with is flow control. That is, it attempts to avoid the problem of a sender just shipping too much data to its local part of the network, even though the global part of the network can't handle that amount of data. Right? All right. So we've talked about transport layer protocol. Question?
Is there a way to make the transport layer detect the size of the packet?
When you say reject the size of a packet, what do you mean? That is, you're trying to send a packet and you realize it's too big, or?
Yeah. So they just say like, reject.
Yeah, well, like here's a dumb algorithm. Send a big packet, 1 megabyte. See if it gets through. If it doesn't get through, then send half a megabyte, right? And so you negotiate that way just by probing the network to see which size packet can get there. No, the application won't notice this. All the application says is, I've got a buffer of data. It's 5,000 bytes or something. TCP will arrange to take those 5,000 bytes, break it into, say, 800 byte packets and ship the packets across individually. But the guy who calls TCP, all it'll see is, the 5,000 bytes got through. And other questions? All right, so next, I wanted to talk briefly about the application layer. So a couple of examples of application layers is for www, we have HTTP. This is the hypertext, I guess that's a capital T, transfer protocol. Another example might be a real RTP, which is a real-time protocol. All right. So the idea here is that, you have web style applications that are dealing with a lot of web pages and controls for web page. They will use HTTP, but not everything on the internet is web-based. In fact, HTTP only has a reasonably small fraction of data on the internet. Most of the data is something else. It'll use a real-time protocol, or most data on the internet now is video data. So it'll be using a video protocol. And so these are two examples, but there are, dozens, hundreds more of application level protocols. It's not that these protocols talk about a single application. It's not like we say, okay, Chrome will have an app, that's an application. Let's have a Chrome protocol, okay? More typically, it's for a class of similar applications. So Chrome uses HTTP, but then so does, Firefox, so does Edge, so does a bunch of other browsers. So the intent here is to not sort of support a single vendor or a single application, but to support a class of related applications. All right. So let's take a look at HTTP, since that's sort of the main protocol, or the original main protocol used on the web. And so this was designed by Tim Berners-Lee in CERN in 1991. CERN is the leading physics research institute in Europe. They do high energy physics. They're, throwing protons at each other and hoping that they collide and that sort of thing. And the problem that Berners-Lee was trying to address was, we have all these scientific papers, all these physics papers, and we want to make it easy for physicists to read the papers. When he was working at the time, the way it was done was pieces of paper, right? You wanted to read a physics paper, you would maybe download it via FTP and then print it out and then read the printed paper. And that, of course, works, but it's kind of awkward and slow and it chews up paper. He wanted to do this just on the screen, right? So he invented the notion of the World Wide Web, or WWW for short. And the web, in this case, was the idea that he wanted each physics paper, when it referred to another paper in a footnote, for that footnote not merely to be some text that you could read and go look it up and go to the library and all that sort of thing, but he wanted it to be a footnote that you could just press on the button and see another physics paper. Right? Either published by the same institution or perhaps by a different institution. And of course, now you have the universe of all physics papers, and they're all pointing to each other because they're all referring to each other. Presumably, you don't have cycles, but I don't know, maybe you do. Why not allow cycles? So you can think of this as being a network or a spider web of physics papers, and that's was supposed to be the World Wide Web when he invented it. Now, what Berners-Lee did was he had this abstract problem, and he glued together two already existing sort of solutions to attack this problem. So you can think of the World Wide Web as being sort of two ideas glued together. First is, let's take TCP, and we'll build another protocol, so TCP plus something or that sort of thing, but a protocol like TCP to transfer physics papers from a server at UCLA to a reader in London, that sort of thing, plus another protocol, except this is a data protocol, SGML. So let's talk briefly about SGML, which is the standard generalized markup language. The basic idea of SGML is you have a bunch of publishers out there. You have Addison Wesley, you have Pearson, you have McGraw-Hill. They're all, printing books and articles and that sort of thing. And these publishers each had their own way of specifying exactly what's going to be in your paper, right? So some of them would take Word documents, but not very many, because Word is like horrible, right? It's a very bad layout engine. It's good enough for business applications, but it's not very good for scientific papers. Some of the publishers would take LaTeX, which looks nicer, but not as many people know it, and all that sort of thing. And it was kind of a mess. So what the publishers wanted to agree upon was a standard interchange language for publishers. Of books and papers and that sort of thing. So instead of one guy saying, well, if you want to start a paragraph, you put a .pp on a separate line. And another guy says, no, 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 what I want you to do is say \para, and so forth and so on. Instead of that, you just have a single standard way. And in SGML, that standard way of doing a paragraph was like this. You'd put a P in angle brackets, and then you have the body of the paragraph. And then at the end of the paragraph, you say the paragraph is over this way. Angle brackets, but a slash in front of the P, right? It's just markup. In some sense, it's arbitrary, but it was the one that the publishers picked. And what Berners-Lee decided to do is, if we want to put papers online, let's just pick this technology, since it's a publisher standard, and let's ship it across the internet via TCP. And let's provide a way to do links, right? So he was gluing together existing technology, but doing it in an innovative way. And that's why, he's now Sir Tim Berners-Lee and all that sort of thing. It was, the physicists loved it. It became commercially successful. And the World Wide Web, started the .com boom and all that sort of thing. So let's take a look at this first part here, TCP+. Now, TCP is just a general technology for building streams. He needed a particular technology for shipping web pages. So he developed the protocol HTTP, which is, let's figure out how to get web pages over the internet. And it's a client-server protocol. So the client opens up a TCP connection to the server, and the client issues requests. And the server, obviously gives you responses. So here's an example of a request-response pair. All right, first, you would say, you open the connection, and then you say something like this: get /index That's supposed to be the word index.html. And then HTTP/1.1. All right. And then also an empty line, right? So here's one line, here's the next line. So the client will send a request. It's this set of bytes. And then, you know, there's actually a carriage return new line at the end of each thing here, because that's what the network protocol says. And these bytes are sent by the client to the server. And what the server does is it responds with the appropriate information. So the server might say something like, you know, 200, okay. And then here's sort of the contents of the web page, right? Web page contents. But in between the first initial response and the actual contents of the web page, the server will also respond with some metadata about the web page. And the metadata will have some very simple things like, you know, a length field, which will tell you how many bytes are in this web page. But there will be other metadata that the client can also use in order to figure out how to interpret the web page contents. For example, there will be a content type field that will say probably HTML, but it might say something else. In case this is an image, it will say, oh, it's not an HTML data. It's going to be, I don't know, PNG data, all that sort of thing. There can be other things, for example, content transfer encoding, which will tell you whether this web page is UTF-8 or something else, right? So the idea here is that this meta information is going to give you useful information about the web page before you actually see the web page. And then by convention, there is an empty line between the header and the actual web page. So in some sense, this is a really simple protocol, right? You send a request via TCP, you get a response back via TCP, and actually in the very first version of HTTP, which was HTTP 1.0, that's all you could do. You could only send a single request, you got back a single response, and then the connection dropped. It was like the simplest TCP protocol imaginable because, you know, Berners-Lee was trying to solve a big problem. He didn't want to make it complicated. Now, with time, this protocol has evolved. And so, for example, HTTP 1.1 extended the protocol to let you issue several requests and get several responses, right? So you can do multiple request responses. And it lets you do a whole bunch of other things too, right? But at this point, I see I've run out of time. So what we'll talk about next time is sort of the evolution of HTTP and how it will give us extra things that will let us, you know, do pretty fancy stuff. We're going to have a midterm review in discussion session tomorrow. So please come. The review will be of old midterms that we've done in the past, and it'll give you practice for what you can expect to see in the midterm a week from today.